my name is Justin Ferguson. I am a technical specialist with Autodesk, and I am here to present robots and productivity. Many say that robots are the future. We ask the question, though, why are they the future? What are the reasons that allow us to make these predictions and influence the future? The purpose of this presentation is to enable you to think differently about robots and to consider robots and offline programming as a way to improve your productivity. Maybe we need to take a quick step back and learn a little bit more about robots. What do robots look like? And what will they do in the future? Robots is a general term that signifies a machine that's able to do work on its own with or without pre-programming. Robots can be scary, like the Terminator, or very useful, such as this Explorer robot driven by a remote. They can even be built to mimic the human body, as you can see in this second image. These robots are able to help us now and will do so in the future. But what are these robots actually accomplishing for us? Both of these are research projects and are designed to be able to do a very specific task. For instance, go into a building that's unsafe and look around. We do a lot of making in this world. These robots aren't actually helping us make anything, even though they are a great help to this world. Industrial robots are designed to help us make things. They have the ability to do repetitive tasks that we humans may not want to do or cannot do. We can see these robots in our technology center, Birmingham in the UK on the left, and the Boston Technology Center on the right. These are able to do tasks such as large-scale milling and large format 3D printing. They're very much like a CNC mill or a desktop 3D printer. So why would we actually look at these robots instead of a larger CNC or a larger 3D printer? In machine shops and production environments, one question always seems to arise. Are we being productive? As a follow-on to that, we ask another question. How can we be more productive? We can then progress to asking more specific questions, such as how can we achieve higher productivity with robots? We've had a brief look at robots, but we need to diverge for a moment and ask questions that have come up, such as what is productivity? Expressed as a ratio of an aggregate output to a single input, or in a manufacturing sense, what can you make with the finite resources that you have? So then the next question, what is increased productivity? It's going to be different for every single company, but a few examples might sound like making the part faster, reducing your upfront costs, reducing floor space, a smaller workforce, or many other possibilities. So how can robots, and industrial robots specifically, allow us to have an increased productivity? We shall return to the intent of this presentation and discuss the reasons we would choose a robot instead of a CNC or a standard 3D printer. We'll dive right in, talking about an example where robots have helped to improve productivity. This is a portable office, which is part of a new construction technique called prefabricated modular construction. Each of the pieces of the office are created as individually complete and only require a small bit of assembly on site to have an office. This is what we call the prefabrication portion. The modular portion allows for expansion simply by adding and connecting the individual offices. We'll go through the process of required to manufacture the front wall of this cabin. The other walls, the floor, and the roof will follow the same process, just tailored for that specific component. The current manufacturing process for the front wall starts as a sheet of laminated material. There's a protective outside and an insulating core that allows us to protect from the elements such as rain, sun, heat, and cold. This sheet is loaded onto a CNC router that cuts the windows and the doors and drills the holes where it attaches to the other walls and also the supporting structure. Next, the outside dimensions of the wall are cut so that the panel is at its final shape. The last thing to do for this finished wall panel is to remove it from the router, and a new blank can be put in its place. One of the reasons this method is used is that it can be very fast to produce a single panel, and it's very repeatable. As you can see, we've moved the front panel model into our software PowerMill to be able to program the toolpath that will drive our CNC machine. It's a very simple workflow. Start by choosing the toolpath that we will use to cut the profile of our part. And then we follow the linear workflow from top to bottom to be able to align the tool to a specific z-axis or our toolpath work plane. We'll choose our machinable area, which in this sense is the entire part. We'll make sure that we have the correct tool, and then move to our settings page to make sure that our tolerances and our actual cutting location is defined. When we press calculate on this toolpath, what we're going to see is that our toolpath shows up as a cutting move in green, and that our red dashed sections are rapid moves from where the toolpath starts and in between each of these sections. Now, one thing that we can notice here is that our lead in and lead out moves for these toolpaths are in a different color as well, and these can be modified outside of the toolpath if we need to change them. Maybe this height needs to be a little bit higher so that we have a little bit more clearance for our tools. So if I make this, for instance, 150, when I press apply, we can see this automatic update for a longer lead-in. Now, putting this toolpath on the CNC machine to watch the simulation, we can see that tool and the motion that this machine will take to be able to cut the outside profile of this part, as well as cutting the windows and the doors. As this finishes up, we will note that this toolpath had no issues throughout the entire part on this first panel. Now, this machine is very long, so we have put a second panel on to this bed of this machine to be able to cut it. Now, this is a very long machine, and what we'll see is that at a certain point, we actually run out of travel on this machine, even though it is so big. This warning message that has popped up has let us know that we have exceeded the maximum travel of our machine, which is 8 meters, by a little bit over the 8 meters. Now, looking at that issue that's brought up in our simulation, we can actually see the simulation and the area that our machine is able to reach. So in a sense, this is a great way for me to predict whether this is going to work on the CNC that I have. In this case, if the panels change size at all, then we may not be able to fit them on this machine. Now, if they do get smaller, that's very beneficial to us. But if they have to modify this to be just a little bit longer, we may not be able to squish them, and we may have spent lots of money to be able to only cut one part at a time. So as we've seen in PowerMill, this is a far improved process from measuring and cutting these holes out by hand, even if it may be power tool assisted. Cutting on a CNC also increases the repeatability substantially, as the tolerances of a machine are much less than that of cutting these panels by hand. There are still a few downsides to this process though. As we showed, the sheet size in the blank, the router needs to be large enough to cut the entire panel. Because of this, the large panel, it results in a much higher cost for the router. The router can only cut one wall at a time. I did show that we did have the possibility to show the two panels next to each other, but this still requires an operator to switch programs and possibly change the setup if we have to change from the front panel to the side panels, or to the roof or the floor. One last downside is that the router is not able to cut while someone, a human, is loading or unloading the material. Think about these things, and we'll have a look at the areas where robots excel and where we can see them help in this situation. In this next section, we will look at areas where the robots can excel. From the working envelope to adaptability, robots have the ability to increase productivity with a bunch of other possible areas as well. In the world of traditional machine tools, the envelope size is exponentially linked with cost. That 8-meter machine is going to be so much more expensive than something that's only 4 meters long, for instance. To achieve the envelope size similar to the ones seen in this image would be many hundreds of thousands of dollars. In the case of robots, large working envelopes can be enjoyed for a fraction of the capital outlay. Robots don't necessarily need to be big enough, though. Smaller robots can actually be just as beneficial due to many other factors, which we'll see in the coming slides. Irrelevant of the specific job or task, hostile work environments are places that humans don't want to be. Think for a moment about situations such as working with a radioactive or other toxic material. Just being around these and interacting with these materials can cause serious injury, or even worse. How about working on another planet or in the vacuum of space? These are just a few examples to look towards robots as a solution. Now, robots still need some amount of human interaction to be implemented, but the work in the hazardous environment can be avoided. Reducing or eliminating exposure to these toxic materials can reduce the cost and even possible problematic outcomes. So why do robots excel in hostile environments? It's due to their freedom of movement. Technology and manufactured parts become more complex and intricate. And with this, we rely more and more on automation due to the ability to move the objects more freely in ways that humans can't. Take, for example, large or heavy equipment such as bulky spot welders. This can decrease the time to make a specific part and also allow for optimization, which can be seen as an increase in productivity. We will also strive to increase reliability by reducing the tolerances on manufactured parts. The robot seen here can help us in a key aspect: repeatable movement and processes. The welds are, for the most part, going to be in the same place on the car every single time. Manufactured parts are not the only place where repeatable movement is desired. With the growing awareness and adoption of robotics in all aspects, we are starting to see other industries, such as film and video, utilize robots to have repeatable camera motion while filming a scene. This allows set pieces to be moved, tweaked to get it just right. This also allows actors to perfect their movement or their lines in scenes where that camera is moving. Optimization and perfection in repetition is another way to improve productivity. This not only is a great example of repeatability of movement, but also the versatility of industrial robots. They're not just for manufacturing and can be used in a lot of different industries. We've seen examples of welding, printing, film, and we'll see more. With the robots used to aid filmmakers, we will note that not all scenes are actually inside a studio, and this brings us to our next advantage, which is mobility. Mobility is a key aspect of robotics, which is mainly due to the initial small footprint compared to the working envelope of the robot. Industrial robots can be mounted in almost any orientation as opposed to a CNC or a 3D printer that relies on gravity. This container was created with two robots hanging on a rail and also a rotating table beneath them. This container is easily transported as a microfactory on the back of a truck or a lorry, depending on where you're from. This set of robots is purposed with directed energy deposition end effectors, specifically WAM, wire arc additive manufacturing, intended to work together as a team to produce metal components quickly. These can be critical components on a construction job site or a repair component where shipping the replacement would take far too long or be just too costly to ship. Think about being in the remote center of a desert or in the middle of an ocean. Both of these are examples of just-in-time manufacturing. Another example that joins a few of these is portable building robots. It's a test here on Earth for printing habitats in other worlds, bringing together mobility and overcoming hostile work environments off-planet. I mentioned earlier the end effector of the container robot. You can see it here close up. Notice there's actually two parts on this end effector. The first being the Wham Stinger on the left side, and the second being a plasma cutter on the right side. Adaptability, which is nearly synonymous with versatility, but in this sense, it means that because the end effector of the robot can change, it's very easy to repurpose this robot to perform another different task. This example shows two tools on the robot end, but there's also the ability to change the end effector on the fly, such as that in our technology centers. In our Boston Technology Center, there's the robot pictured here that has 5 different end effectors that can be swapped out just by issuing a command in the control. Each of these has a different use for this robot. In this case, the robot is used for constructing wood structures. So the end effectors are a gripper for pick and place, a saw, a nail gun, a drill, just to name the few. It's easy to start to think about how a robot can improve your productivity. What are the key aspects in our example that we can use to increase our productivity? Let's have a look. Utilizing the robot on a rail, we can actually optimize some of the floor space where these panels are being produced. We can also change the orientation of the panels to further reduce floor space and make it easier to load blank panels and unload the finished parts. Having the ability to move the robot on the longer rail gives the ability for 2 or more setup areas. This means that multiples of the same part can be cut at the same time, or alternatively, multiple jobs can be set up at once. For instance, cutting one of each of the walls. A cell could feasibly complete all of the wall sections required for a modular office in one cycle. Both of these ways will improve productivity. You'll remember that we showed how easy it was to create that toolpath in PowerMill and the ability to simulate to see issues before we send this program to the shop floor. To demonstrate what these processes look like for the robot, we're going to step back into PowerMill and show the comparison of the size on the router, robot programming, and also the simulation on the robot. In this case, we've overlaid and superimposed that router on top of our robot. And as we can see from this view here, our robot with 2 walls is just slightly wider than our mill. And if we were to look at the left view, we can see that they're really pretty close to the same length as well. We do save a little bit on the height, but for the most part, we can come to the conclusion that for the same amount of floor space of the router, which we were having trouble fitting 2 components, we could fit a lot more. So now that we've actually put the part on the robot, we can see all of the extra space on that wall to put more components. We're going to start with programming just one small toolpath for now, which is the upper edge of our front panel. With this, on our right side, we can see our vertical plugin window has the robot controls, where I can attach the tool to the start point and then press play to watch that simulation. Now we do see that this robot is able to machine this entire component without too much movement, but it may not be the most optimized movement that we want to see for this robot. We can utilize that linear rail to be able to reduce a lot of the motion that that robot sees. Changing the priority of that axis to high and reattaching that tool, we can see that there's a lot less motion of that robot to cut that top portion of the panel. We would then save this simulation and load it into an NC program to then send to the robot. I want to talk about a quick digression real quick, because one of the ways that robots can definitely speed up our process and make it a little bit better is the ability to just turn the tool and be able to utilize a saw to be able to do the cutting. So if I zoom in real quick, we can see that a saw blade is going to be able to come in and cut that top edge very easily and very similar to the previous component, but it's going to give us a nice straight edge. Similar to the previous way we did this, we attach it and press play, and our robot is going to have a similar motion to the one that we had prior. If I reattach it and change that axis priority and press play, we can see that we do get that nice, smooth, much smoother motion on that linear rail, just to keep the robot static and move that tool. This is another way that we can think about other tools that will help us improve productivity that may not be available on a CNC mill. So quickly, I'm going to step into another project where I have all of these panels put together. And I'm going to work my way through to the robot program where I can right-click and add toolpaths. So we'll start in this case with the upper edge and add that toolpath. At this point, we can use our window at the bottom to be able to view how the robot is going to move along the path to get to our start point of our toolpath, and then actually machining of that toolpath. What I did is I actually have this as a saved program. So I will just load all of the different portions of toolpath that will be required to machine all of these different panels at the same time. With this, I can see that my toolpath is going to step through and actually start to do the drilling as the first portion of this toolpath. And it'll move along from panel to panel to panel, reducing the number of tool changes required and doing all of the drilling operations followed by the milling operations. Stepping through this, we can see the different areas where the programming steps have changed to be able to follow along with our part. Once the tool change happens, we then are able to machine the door and window components and move point to point to point and have our simulation where we can see if there's any issues before we send this to our machine on the floor. So we've seen the improvements that can be made in changing from a router to a robot. But what else can we work on to improve our productivity? One way we could introduce our scanning or probe inspection during the manufacturing process to allow for quality monitoring. A second method might be to change the end effector of the robot to be able to automate the loading and unloading of the finished components and the raw material. This would allow for a truly lights-out manufacturing cell. What about other methods? Can you think of any? We've got a few case studies to follow that we have worked on that may help you ponder on this a little further. In the next few slides, we'll see the following areas where the robots have helped increase productivity. The first one we're going to address is polishing molds. The second, Lassim, which is a large additive, subtractive, combined machine. We'll then look into airfoil blade polishing, and lastly, robot milling or sculpting.
My name's Sam Wilkinson. I work in the Specialist Modelling Group at Foster & Partners.
I'm Josh Mason from Foster & Partners in the Specialist Modelling Group.
Foster & Partners is a global studio for sustainable architecture, urbanism and design. Over the past decade, we've been investigating advanced structures and material optimization, the use of steel, concrete and plastic for large-scale additive manufacture, and technologies behind this, such as robotics and digital design software, and other technologies needed for future applications like extraplanetary habitats on the Moon and Mars. Which brings us to Lassim, which is an EU-funded research project with a consortium of universities and companies. Lassim stands for the Large-Scale Additive and Subtractive Integrated Modular Machine.
As part of our role on Lassim, we designed a high-performance steel cantilever beam, taking inspiration from Maggie's and Crossrail. As well as being a driver for the design of the machine, we wanted the part to be adaptable for different sizes and structural loads for mass customization, and to illustrate the internal structural behavior of a cantilever beam. We have been developing new approaches to structural optimization and generative design, and experimented with generative Autodesk software.
The mission of the project was to develop a hybrid machine, one of the first, combining additive and subtractive manufacturing with the extended capabilities needed for surface treatment and inspection of the parts being manufactured. The Lassim system is based on wire and arc additive manufacture, WAM, which has a relatively high deposition rate, up to 10 kilograms per hour compared to other 3D printing technologies. Our role at Foster & Partners in the consortium was as an end user, where we worked with Autodesk and the other partners to develop a new design approach incorporating all the manufacturing constraints and a demonstrator part to show its potential application in the construction sector. The aim of the consortium is to make fundamental steps towards transforming the construction industry by developing new manufacturing technologies.
After Lassim, our next steps will be focused on developing the supply chain to deliver at scale on live projects and pushing the software to analyze and generate complex geometries. With Lassim, combining everything into one machine, we were able to truly develop additive and subtractive, which gave much more interesting opportunities for shape and form.
So in this next example, the blade polishing, we can see that this robot cell is fully automated. The robot comes, picks up the part off of a conveyor, moves it over to an inspection probe where it actually inspects the part to see if it is at the correct size. Once those results are processed through computer automation, we actually then do the program for this specific blade to do the polishing. This is then simulated to make sure that it is correct and then run on the machine. Again, a fully automated process. Once the blade is fully polished and finished, a second inspection is done to verify the work, and then the blade is replaced to then start this entire cycle all over.
Merlin Entertainments is an entertainment business that we support from here, based in Alton Towers, called MMM Studios North. This particular site has been here for 25 years, servicing the theme park and resort industry.
We get pulled in from all across the world to bring these themed environments to life.
I think what makes Merlin Entertainments unique within the business is the array of brands that we deliver to the general public. We're dealing with more and more key brands now in the marketplace, and being able to deliver exactly what they give us, as in their image or their expectations. The whole process of using PowerMill has been able to enhance that and help us do that.
Everything that was made for attractions was done by multi-skilled, highly skilled professionals like sculptors and prop workers and joiners. These skills are getting increasingly difficult to get hold of nowadays, and even more so when you're dealing with IPs.
What they give us as a digital file, we can program into the machines and they cut. So what they give us, they get. So there's never any argument now over pose or posture.
When we're using PowerMill, it's brilliant. We import our model and that is it. We are cutting that model that they have given us. So it works perfectly with it. You know, it helps us get everything right and to how they want it.
I think the key component to delivering projects is down to the staff and their total commitment to the product and the Merlin brands.
You have to immerse yourself within it to make sure it's the best product it can actually be at the end of the day. A lot of people that work here have children that love the shows that we're working on, and we're just desperate to make sure that comes through and we produce a product that is that good.
I think Autodesk enhances our whole business, certainly at the front end, through our joinery and sculpture departments, where it's totally mechanised the whole of our production and the way we deliver the product.
It's made a world of difference. We no longer have that element of, is this right, is it wrong? We can get the asset files straight from IP holders and produce those characters exactly as they should be, which means we're happy, the clients are happy, the IP holders are happy, and we can move on and really make a really good themed environment.
Before we made the leap into the digital age, we spent many months looking at different packages. We found that Autodesk delivered the best for us.
Working with Autodesk has been fantastic. We're really excited to see future implementations of 3D printing and seeing how the software collaborates with that. And also the cloud system. Other offices within our business can collaborate all on one project at the same time.
ArtCam and PowerMill have been the saviour of this business in the last 4 years, because I think if we hadn't moved with the times, we'd be out of business because we couldn't compete.
For anyone considering Autodesk, I'd say jump right in.
I think PowerMill and ArtCam are the way to go, certainly within the 3D modelling industry.
They put out a fantastic product, the support's there, the overall package is just definitely worth going for.
So after seeing the possibilities to increase productivity with industrial robots, it's quite easy to see the bright future and the many ways that industrial robots can help you now. I want to thank everyone for coming to this presentation on robots and productivity. If you have any questions, feel free to reach out to us. Other than that, I can stay online and answer any questions that you might have. Thank you. Have a good day.